Welcome to Section 1.3. This section's on vector equations. We'll look at adding and multiplying by a scalar. We'll understand the geometric interpretation of vectors in span. And we'll look at algebraic properties of Rn and try to understand linear combinations of vectors. So first of all, we represent vectors as arrows in the plane. And here's u as a vector 3, 2, which actually means, I'll go ahead and go to part 2 and draw u. It means go over 3 and up 2. And so we get to this point, and then we just draw an arrow from the origin 0, 0 to that point. We can also draw the vector v, which is going over 1 and up 4. And so if we want to add u and v, we add vectors component-wise. We write down u as the top and bottom plus v as the top and bottom, and then we simply add the top components and we add the bottom components, and that's going to give us 4, 6. And so let's go ahead and draw that in the plane. So this time we go over 4 and up 6. And one thing you should notice is that when you draw in, so we have u is that purple arrow, and then we have our v is our pink arrow. When we draw another copy of v where we start at the arrow from u and go up, we get to u plus v. And similarly, if we do v first and then draw the arrow u coming out of v, we also get to our vector u plus v. And you notice they kind of form a nice little parallelogram. So there's a relationship between those. So that's how you add vectors geometrically. We can also multiply vectors by constants. So if we take, for example, 2 times u, that literally means just multiply each entry in u by 2. And same thing for negative 2/3 u. That's going to end up giving us a negative 2 and negative 4/3. And so we can draw these as well. If we do 2 times u, you'll notice that that's essentially the same thing as taking our vector u and literally just lengthening it. So this is 2 times u and negative 2/3 u. We go over, in the negative sends us in the opposite direction. And then the 2/3 tells us how far to go in that direction. And another way to think of a vector is it's both a direction and a length. Okay, so we can also talk about reflecting vectors across axes. And here, if we reflect u directly across the x-axis, so we have our x-axis here, if we take this vector and we kind of reflect it across, what we're going to end up getting is the same x-coordinate, which I guess here is 3, but our y-coordinate is negative. And now we'll pause for our first quiz so that you can look at what you will get the first quiz question today asks us, can you get to the vector 5, 2 by simply adding together something times u and something times v? So think carefully about this before you answer, and remember, these multiples don't have to be whole numbers. Okay, so sometimes I don't give you the answer to the quiz, but today I'm going to go ahead and give you the answer now that you've taken it. If you try to make 5, 2 by taking something times 3, 2, plus something, plus something times 1, 4, we can actually write that as an equation, because we think about, we want that 5 in the top needs to be 3 times something plus 1 times another something. And similarly, the 2 in the bottom has to be 2 times that first something plus 4 times that second something. And so now we have a system of equations. And moreover, we can use some of the algebra skills that we've done before. This is a little bit of a preview in some sense of what we're going to be doing. Let's multiply the top equation by 4, because that gives us a 4b. And then the bottom equation, we can keep it the same. And we can subtract the bottom from the top. And we get 18 equals 10a. So now we know that a equals 18 tenths, which we can divide by 2 and make that 9/5. And so actually we could just plug this back in to figure out what b is, because we have 5 equals 3 times 9/5 plus b. So b is going to equal 5, which we may as well make that 25/5. Minus 9 times 3 is 27, and so b equals -2/5. And you can check now that, in fact, if you do 9/5 times 3 on top and 2 on the bottom, and then subtract out, oops, I wrote a 3 there, but that should be a 5, 2/5 times 1 and 4, you will, in fact, get 5/2. Okay. So now let's talk about a new definition, and that's called a linear combination. So a linear combination of vectors is where you take the vectors and you multiply each one of them by a constant, and then you add that up. So if you try to think about a linear combination of 4, 2, and 6, 3, we're looking for something times 4, 2, plus another something times 6, 3. And if you think about it for a little while, and maybe you can pause and think about this and see, can you come up with a vector that you can't get by this process? If you do that for a little while, you'll notice that whatever you get, you're still going to, whenever you multiply 4, 2 by something plus 6, 3 by something, you end up getting something where the top number is always twice the bottom number. So in fact, anything that doesn't satisfy that, 1, 1, for example, or 2, 0, 1, 3, 4, 3, etc. Basically anything that doesn't have twice the top on, let me write this in a nice way. Anything not of the form number on bottom and then twice that number on top. And if you play around with equations, you'll kind of see why. Okay, so we have another quiz question. And this quiz asks you to give an example of 3 vectors u, v, and w, and a 4th vector x, such that you can't get to x as a linear combination of u, v, and w. Okay. So again, I'm going to go over the answer to this particular quiz question. Well, there's lots of different examples, in fact. If we take u equal, let's think about 2, 1, and let's take v and w, the same vectors that we saw up above. All of these are going to be of the form 2 times, the top entry is 2 times the bottom entry. And so if I take x to be something that's not of that form, then we just can't get to that x using linear combinations. And this is kind of going to bring us to the notion of span. And we have, let's see if I can do this on the same page. Yeah, okay. So formally, the span of a set of vectors is just all linear combinations of those vectors. And so in fact, if we look at these 3 vectors, we have, let's see, u is 2, 1, and then let's draw v in blue, that's 4, 2, and then you notice that w is also just 3 times u. And so really what we've done here is we've multiplied these vectors. We started with a vector 2, 1, and we just multiplied it by different numbers. And so we're not really getting off of that particular line. I've listed several algebraic properties of Rn. So, and hopefully you've also done your reading. So Rn, okay, let's see here. Okay, so Rn is all vectors of the form A1, A2, up through an. So basically it's vectors that have n coordinates. We're used to thinking a lot in 2D and sometimes in 3D, but our n means we're in n-dimensional space. But the properties it has are kind of similar to properties you're used to. U plus v equals v plus u, so that's commutativity. And that's the property that you can kind of see when you go back and look at our parallelogram. Well, if we did u plus v first, we get this blue vector. But if we did v plus u first, we still get that same blue vector. And so one good way to make sure you really understand these properties is to go back through and kind of think about what they mean geometrically and see if you can understand why they might be true based on pictures of vector addition. So here we have the distributive property. We have a 0. We have something called additive inverse. Sorry, that's not distributive. If you, let's see, let me go and write the additive inverse. That is the associativity property. And the distributive properties, we got 2 of them, they're down here. So these properties that you're probably used to when working with real numbers turn out to also work for vectors. And we can use them to prove things about vectors. So we're not going to focus a lot on proofs in this class, but we will do some basic proofs, and I'll try to talk about the proof techniques that we're going to do. This first thing is really applying properties, and if you ever had one of those geometry, like 2-column proofs, maybe in high school geometry, this is that same idea where we make a statement and we make a justification. So let's say we have a whole bunch of vectors. So we have W1, 2, and 3, and we also have U and V. And first of all, we have that U and V are in the span of W1, W2, W3. So, and then it's asking us to prove that their sum is also in that span. So our very first step on this is to just use what we know. So we know that U and V are in the span. And remember, we go back and look at our definition, and oftentimes a lot of what a proof is writing out your definitions. So we know that U is something times W1 plus something times W2 plus something times W3. And similarly, V is a different something. It's important to use times W1 plus another something times W2 plus another something times W3. You don't want to ever reuse variables because that would assume that's the same variable. And since U and V are different vectors, we want different coefficients of our W's. Okay, so now we want to prove something about their sum. So let's go ahead and write down their sum. So U plus V, we want to understand what that looks like. Well, let's substitute. So we know that U is A1 W1 plus A2 W2 plus A3 W3, and V is B1 W1 plus B2 W2 plus B3 W3. And now we see W1, 2, and 3, but what we want is some number times W1 plus some number times W2 plus some number times W3. And right now we have like a W1 showing up more than one time. So the first thing we want to do is try to group those W1s together. And we can do this because we can commute that B1 W1. We can move it over using that very first property of Rn. And so we can do that same thing for our W2s. We can move the B2, W2 over in front, and same thing with the W3s. And so we want to let the reader know which property we use to do that. Okay, so next, we're getting somewhere. Now we only want to see one W1. Right now we see two, one with an A1 in front of it and one with a B1 in front of it. So what we want to do is the very natural thing of using the distributive property to regroup it. And that's exactly what we do for each of these. We just have to make sure that we write down that in fact we did use that distributive property, and let's think carefully about which distributive property. So we had two different constants, so that's C and D, rather than two different vectors. So we're going to use property 6 for this. And that is enough to give us each of our vectors has some constant in front of it. Because since A1 plus B1 is in R, A2 plus B2 is in R, and A3 plus B3 is in R. And so we've completed our proof, and I usually like to make a little, and I usually like to make a conclusion. So before we draw a little box, let's say, so U plus V is in, and there's a little E symbol that we often use to mean in, and then the span of W1, W2, W3. Okay, so our next quiz question asks you to draw the span of the vector 1, 1 in R2, and then it just asks what geometric object is this. Oops, okay. So hopefully you felt pretty comfortable about the span of one line, and in general, anytime you have one geometric object, one non-zero vector, even if you're in a three-dimensional space, what happens, like let's say we have our vector coming out here, the span is just all multiples of that vector. And so you're just going to start multiplying it, but you're still going to go maybe in a forward direction, maybe in a backward direction, but you're always going to get a line whenever you take the span of just one vector. Our final quiz question for this particular section asks about the span of the vectors 1, 1 and 1, 2. And I'll give you a little hint to start with. So first of all, we have 1, 1 goes like this, and 1, 2 goes like this. Maybe I'll draw this in a different color. And you want to start thinking about multiples of these. And you know, if you take like 2 times 1, 1 and you add it to 1, 2, then you're going to get, you know, something that goes like this. So you're going to start getting things that aren't just in one of those two lines. So I will pause now and let you think about the answer to that. Okay, and now finally, when we're in R3, we're still in three-dimensional space, but if we want to have a line, well, we just want to write down two vectors that are still, one of them lies on the, so if we take this first vector, 4, 1, 3, its span is just a line. And so if we want to take a second vector and not go off of that span, we better just make a multiple of that first vector, so we stay on the same line. If we want to get a plane instead of a line, then we just need to get two vectors that don't lie on the same line. For instance, 1, 0, 1. And now what's interesting is if you take three really different vectors, you're going to get a three-dimensional space. But if you take, let's say we take these two vectors that lie on different lines, so they together span a plane, and we take like a multiple of one of those vectors, well, then we haven't really given ourselves the opportunity to get off of that one plane. But even more than that, we can do something a little bit fancier and still stay in a plane if we take our vectors 4, 1, 3, 1, 0, 1, and let's say we take the sum of those. So 4 plus 1 is 5, 1 plus 0 is 1, and 3 plus 1 is 4. Well, that vector 5, 1, 4 was sort of in the span of 4, 1, 3, and 1, 0, 1. And I shouldn't have said sort of there. It is in that span. And so that means that we're not going to, that 5, 1, 4 isn't going to be a ticket off of that plane. So this is another example of 3 vectors in R3 whose span is still just a plane, a 2-dimensional thing rather than a 3-dimensional thing. And I think we'll stop there.